Imagine a world where energy was so clean and abundant that it was no longer a limiting factor in the growth of civilization. Governments, research organizations, and companies all across the world are racing to achieve a fusion power breakthrough. It would mean the end of fossil fuels, a technology so impactful, its invention could be compared to man's earliest control of fire. Many critics say it's impossible, but one company believes they've cracked the code.
So David, are you building a machine that will produce cheap, clean, abundant energy in our lifetime?
That's the goal. So Helion Energy is building fusion generators. Our goal is to build 50 megawatt scale generators that generate clean, safe electricity.
According to Helion, your home might be powered by fusion much sooner than anyone expected. But why is fusion considered the holy grail of energy? If you could design the perfect energy source, it would have an inexhaustible supply of fuel, be environmentally friendly, not take up much space, and have a high degree of safety. Fusion power, an experimental form of power generation that harnesses the energy released when two atoms combine, fits the bill. Research into fusion power began in the 1950s, and scientists have been able to fuse atoms in a laboratory setting for decades. But no one has yet been able to demonstrate fusion in a practical way to generate electricity. The potential is enormous. Just 1 gram of Helion's fusion-fueled deuterium contains enough energy to power a home for an entire year, and its supply is virtually unlimited, found in small concentrations in all water on Earth. The fuels considered for fusion power have traditionally all been isotopes of hydrogen, protium, deuterium, and tritium.
And what we saw is that there's some better fusion reactions, and deuterium and a rare isotope of helium called helium-3, and you fuse those together and you make helium-4 and a tremendous amount of electricity.
But what is nuclear fusion? How can just 1 glass of anything contain as much energy as 10 million pounds of coal? To answer that, we must enter the inconceivably small and impossibly strange world of the atom. The atom is the smallest unit of ordinary matter that forms every element in the universe. Every atom is composed of a nucleus and 1 or more electrons. If we zoom into the nucleus, we'll find it's made up of protons and neutrons. Because neutrons are neutral, nuclei are positively charged. If you heat atoms to high enough temperatures, they lose their electrons, forming a hot cloud of charged particles called a plasma. Atoms are always moving, vibrating, and bouncing around. The denser the plasma, the more likely it is that nuclei will collide, but positively charged nuclei repel each other if they get too close. The hotter the plasma, the faster the charged particles move, and the faster a particle is moving, the more kinetic energy it has. When nuclei collide at high enough speeds to overpower their electrostatic repulsion, they can get close enough to be overcome by a stronger attractive force, called the strong nuclear force, and they snap together. When 2 light nuclei combine to form 1 heavier element, the reaction is known as nuclear fusion. This element weighs slightly less than the sum of its parts. The missing mass, or deficit, was released as pure energy, up to 4 million times more energy than burning fossil fuels. In the core of the Sun, gravity produces incredibly high pressures, compressing elements to densities higher than the heaviest metals and to temperatures over 15 million degrees Celsius. Perfectly extreme conditions for hydrogen to fuse into helium. The Sun is Earth's largest source of energy. Plants convert sunlight into chemical energy with photosynthesis, and we release it by burning fossil fuels. Solar radiation powers the wind that spins our windmills, the rivers that drive our turbines, and we can even convert sunlight directly to electricity with photovoltaics. It's about time we vertically integrate and bring nuclear fusion in-house. But without the benefit of tremendous gravitational forces and 10 billion years worth of fuel, man-made fusion will need to be even hotter and more efficient than the Sun. In a man-made fusion device, you must not only confine a plasma so hot it will vaporize anything it touches, but also harness this chaotic thermonuclear reaction to generate more energy than is being lost to the environment.
And that's the critical parameter of, did you make a fusion fuel dense enough? Are the particles close enough together? Are they hot enough so that they can actually react with each other? And are they around long enough to create a lot of reactions?
It turns out, bottling a star is one of the most difficult technical endeavors ever attempted on Earth.
So I think the hardest part about fusion is that we have a combination of engineering and physics disciplines that all come together, and they all have to work. And so you have not only the complex physics around the electromagnets and the fusion plasmas itself, but you also have these systems that operate at high temperature, high stress, high pressure. And most importantly, you have to do it in a way that's commercially relevant.
Helion's key to solving the ultimate energy puzzle is contained in these purple glowing rings that are fired at over 1 million miles per hour. But there's more than one way to fuse an atom. In fusion, there's 3 key groups of approaches. In magnetic fusion, the goal is to contain a very hot plasma in a steady magnetic field for a long time. until it ignites and forms a self-propagating fusion reaction. In contrast, inertial confinement fusion relies on achieving higher plasma densities. Fusion is initiated by rapidly compressing and heating tiny targets filled with fusion fuel, most often using high-energy lasers. Each shot takes place in 1/1000th of a second.
And there's a third type of fusion called magneto-inertial fusion that takes both worlds, and you magnetically confine and contain a plasma like we do in our field reverse configuration. And rather than trying to hold on to it for a very long time, you compress and heat it, add energy through compression. And in our case, you end up right about in the middle where it all happens in about 1/1000th of a second.
While fusion reactions have been successfully demonstrated by various approaches, this does not guarantee these methods could ever be scaled up to produce electricity in a commercially viable way.
So in fusion, one of the biggest challenges we have is we know how to heat a fusion fuel, we know how to put energy in, and we've watched fusion reactions happen for a long time. The challenge is you need to get more energy out than you put in. And from Helion's point of view, it's even more important that not just energy out, but electricity out.
Heating fusion fuels to astronomically high temperatures requires a tremendous input of power. The first hurdle is to achieve break-even by producing at least as much power as you put in to heat the fusion fuel. So far, none of the 35 private companies and 81 research organizations working on fusion have broken even. But breaking even is not enough. In order for fusion power to be practically viable, you need to extract more usable electricity than it takes to run the whole fusion power plant. To do this, the rate of energy production by fusion must not only exceed the rate of thermodynamic losses, but also produce enough of a surplus to overcome all the various energy overheads in a fusion facility to produce net electricity. To understand how Helion plans on becoming the first to achieve net electricity gain, let's find out what traditional nuclear fission power has in common with most approaches to fusion. In the reactor at the heart of modern nuclear power plants, heavy nuclear fuels like uranium-235 are split into lighter elements, releasing huge amounts of heat. Nuclear power plants have been in operation since 1951, but still generate electricity the same way we've been doing it since the 1800s, using heat to generate steam that spins a turbine connected to a generator. Other thermal power sources such as fossil fuels, geothermal, biofuels, and concentrated solar power all rely on basic electromagnetic induction to convert rotational energy into electricity. Many experimental approaches to generating electricity from fusion function in a similar fashion, but Helion believes they have a shortcut.
So one of the things we pioneered is a new approach for getting electricity out of fusion. Ironically, this is actually a really old idea. In the 1950s and 60s, the pioneers around fusion said, hey, we know all this energy is in magnetic energy and in charged particles in this fusion plasma. Wouldn't it be great if we could extract that in terms of direct electricity from the fusion plasma? The problem is, a lot of the electronics required to do that didn't exist at the time. So it's taken the intervening years for us to understand more of the physics and the power electronics to be able to build the systems we build today.
In 2020, Helion completed their 6th fusion prototype, Trenta. Trenta runs nearly every day doing fusion, and demonstrated Helion could directly recover some electricity from their fusion generator.
And that has been our focus from the beginning is, can we take electricity directly from the fusion fuel, from the charged particles, from the plasma, from the magnetic field, and turn that into electricity directly without steam turbines.
Taking the lessons learned from Trenta, Helion is in the final stages of building their 7th generation prototype, Polaris. The goal of Polaris is to prove Helion can generate net electricity from fusion for the first time. Electric Future was granted exclusive access into Helion's Antares facility to get a never-before-seen look at the construction of Polaris and insights into the science and engineering behind it. The first stage of the process is formation. Tiny amounts of Helion's fusion fuels deuterium and helium-3 are injected as a gas into the formation chamber and superheated into a plasma using oscillating magnetic fields just like a microwave.
So what you're seeing behind me is the tube that we actually inject gas into this system with. So fusion systems operate at high temperature and high magnetic field. And so these tubes require very specific materials. This is made out of fused silica, quartz.
Once the fusion fuels are in a state of plasma, it's time to begin adding energy.
So in our systems, we have these electromagnets that we run large currents, millions of amps of current to compress and heat the fusion fuel. But to get that mega amps of current, we use capacitor banks.
Electromagnets are a critical component of magneto-inertial fusion.
So in a pulsed electromagnet, there's large amounts of current flowing. So that means heating, ohmic heating of the coil itself. There's a large pressure, a large force, maybe on the order of 100 megapascals or more a force that's pushing on this magnetic coil. And so these magnetic coils have to survive both the high temperature, the pulsed nature of it, as well as they tend to operate at high electrical voltage as well.
The capacitors are charged for a few seconds, storing electrical energy, and then in less than 1,000th of a second, that energy is discharged into electromagnets wrapped around the device. The magnets invert the plasma's magnetic field on itself into a toroidal structure called a field-reversed configuration. The electromagnetic properties of plasma are fundamental to understanding magnetic fusion devices. Let's do a basic grade school demonstration. If I heat atoms of helium gas above their ionization energy with this Tesla coil, the electrons are freed from their atomic orbit, resulting in a hot cloud of helium ions and free electrons known as a plasma. Because all the particles have a net electrical charge, plasma is electrically conductive and magnetically controllable. When helion's electromagnets fire, they induce an electric current that flows in a loop inside the donut of plasma. As the current flows around the plasma, it generates its own reversed magnetic field which wraps the plasma. Rather than confining a plasma on an externally generated magnetic field like most other fusion approaches, in an FRC, the plasma is self-organized, held together by its own magnetic field.
And what it allows us to do is pretty unique. In an FRC, field reverse configuration, you can actually compress, heat, move, and translate that fusion fuel. And that's what we use to be able to actually make fusion faster and smaller.
After FRCs are formed on both ends, magnets fire sequentially, accelerating them towards each other at over 1 million miles per hour.
So much like squeezing a tube of toothpaste, it's called peristaltic acceleration. You increase the magnetic field behind the fusion fuel and it applies a pressure and that accelerates that plasma.
Electromagnets accelerate the FRCs out of the initial injector system into the main fusion compression chamber, where they merge to become one large unified FRC.
They actually collide into each other, superheating, converting all that kinetic energy, all that directed velocity into heat, into thermal energy, superheating the fusion fuel and getting it primed to begin compressing and getting fusion reactions out of it.
In the center of the device, the machine's magnetic field is rapidly increased, compressing the plasma with a powerful force over 10 Tesla.
One of the other unique things about a field reverse configuration is that it's high beta. And what that means is that it's high pressure. In a field reverse configuration, if you use a magnetic field to compress and heat your fusion fuel, think about squeezing a balloon. In a high beta plasma, which is very different from most fusion plasmas, the fuel pushes back on you. So as you compress that balloon, increasing temperature and pressure inside the balloon, it gets hotter, it gets more dense, and fusion starts.
During operation, the fusion core inside of Polaris will momentarily be the hottest place in the solar system. The plasma-facing materials that line the inside of a fusion device must be able to withstand thermal loads greater than a spaceship re-entering Earth's atmosphere.
Yeah, so the first wall is probably the most critical part of a fusion generator of any kind, where you have this core that's over 100 million degrees, and you can imagine any material next to that wall won't survive. It will melt.
However, the plasma doesn't touch the wall. Fusion systems operate under a vacuum, and the fusion core is insulated from the first wall by a vacuum boundary. But fusion puts off intense electromagnetic radiation, as well as high-energy neutrons that blast the wall with tremendous power, damaging even the most durable materials. The quest to find the perfect first wall is a key material science challenge in producing fusion power. At 100 million degrees Celsius, the deuterium and helium-3 atoms are moving fast enough. When they collide, they have enough energy to overcome their electrostatic repulsion and get close enough to fuse into helium-4. Helion's unique fusion fuels react in a manner that's particularly conducive to direct energy conversion. While most fusion power reactions release up to 80% of their energy in neutrons, deuterium-helium-3 fusion is aneutronic. When they fuse together, its energy release is carried by an alpha particle and one high-energy proton, no neutron.
The problem with a neutron is that it's not very useful in terms of actually generating energy. It just makes heat, where other of particles are charged particles that you can directly extract electricity from.
All these fusion reactions within the plasma convert matter into new energy, which strengthens the plasma's magnetic field. As the plasma's magnetic field gets stronger, it pushes back on the magnetic field of the machine, causing a change in the machine's magnetic flux. This change in flux induces current in the machine's coils, which is directly recaptured as electricity and returned to the capacitors that originally charged the magnets around the machine.
So our goal is to compress and heat the fusion fuel right till it begins to ignite, and then turn it off. Expand it, get that electricity out of the system, put in new fuel, and repeat the process.
Helion's fusion generator needs a way to exhaust hot gases out of the fusion chamber after each pulse.
So think about the exhaust on your car. In the diverter is where we take the remaining fusion byproducts. Some have been burned, some fused, some unfused. We separate those. We also take the remaining energy that's out of the system and we extract that for electricity. And so it has to deal with some really complex engineering and physics where it has the high temperature gas that's being exhausted from the fusion system. You actually want to then also pump out, you want to remove any air in the system in this exact same geometry.
After each 1 millisecond pulse, Helion's fusion electricity will be delivered to the grid.
What a pulse system really enables us to do is dial what we call rep rate. So I can change if you want to think about an engine, the RPM of that engine, so that I can turn up or down the power depending on what is needed for the load.
Helion's North Star is the delivery of commercial electricity to the grid as soon as possible. So, when does Helion expect to begin producing electricity, and how much will it cost? The availability of fusion fuels is a primary consideration for commercial fusion power, but the amount of fuel used for each pulse is minuscule. 500 milliliters of deuterium is enough for approximately 5.5 million pulses. Deuterium is abundant on Earth, but helium-3 is incredibly rare. It's even been suggested we'll need to mine it from the moon. Because the moon lacks a protective magnetic field like the Earth, solar winds create a buildup of helium-3 in the dust on the lunar surface.
Problem is that if going to the moon is part of your business plan, you already have a lot of challenges to making commercial electricity here on Earth. So to get helium-3, one thing Helion has done is we have patented a process to take deuterium, which is found in all water on Earth, clean and safe, fuse that together to make helium-3, then take another deuterium, fuse that together to make helium-4.
Helion believes commercial fusion power isn't a fundamental physical problem, but an engineering problem that will be solved by building, testing, and iterating fusion systems.
Some of the most important things when we're building these fusion systems, these fusion fuels over 100 million degrees, is the diagnostics. How are you measuring what you're actually creating? And so we inject an infrared laser into here. And add that just like an index of refraction, just like as you put a straw in water and it bends the light as it passes through the water, so you see a straw kind of bend. Same thing happens in a fusion plasma, where the laser passes through and it bends in the plasma, and then we collect it. And by measuring the offset and by measuring the bend, we can measure how many particles it passed through in the process. We also want to directly measure the fusion products themselves. And so we have neutron detectors that measure any neutrons that are made. We have alpha particle detectors that directly measure the fusion particles, the charged particles that come off the fusion reaction.
Helion expects that Polaris will demonstrate the production of net electricity by 2024. But in the realm of cutting-edge fusion, demonstration does not equate to viability. So what's Helion's plan for achieving commercial fusion power?
I would agree that most approaches to fusion, that even though we know the physics and engineering well enough to build systems that can make net energy, they may not be commercially viable. And so you need to answer that every time you're building these systems is what does that end product look like? Can you mass produce this? Can you drive down cost? Can you get it to the market cost effectively?
To accomplish this, Helion approaches production in a way that's reminiscent of Elon Musk's strategy for Tesla. Many experimental approaches to fusion necessitate large scale and high capital costs.
And even though fusion scales really well, so as you go up in radius of the fusion system, you get tremendously more energy out. That's great, and the cost goes down, but the commercial practicality also goes down. So what we imagine is gigafactories of fusion systems, small scale, where we can mass produce these at low cost. And so rather than building big, giant, one-off boutique fusion power plants, you're actually building power plants or a collection of small generators. They come together, and that enables you to actually build fusion systems commercially practical.
So how much will fusion power cost for you, the customer? Helion estimates that their fusion power will be one of the cheapest sources of electricity, with the cost of electricity production projected to be 1 cent per kilowatt hour, or $10 per megawatt hour. If Helion is successful, how will fusion power fit into the global energy mix?
The need for clean baseload electricity is huge. And we at Helion don't think fusion replaces renewable energy. It's an addition.
Energy production, primarily the burning of fossil fuels, is responsible for most of global greenhouse gas emissions. Initially, fusion power can serve as a zero-carbon alternative to fill electricity production gaps in markets that don't have high penetration of renewables, like developing countries. In areas that already have lots of solar, wind, hydro, or geothermal energy, fusion can become the on-all-the-time, industrial baseload source, replacing fossil fuels, and even nuclear fission power. While modern nuclear power plants are the most reliable, zero-carbon energy source on the grid today, fusion power has many prospective benefits over fission. For one, there's lower potential for catastrophic accidents. Because fusion requires precise conditions that are difficult enough to create intentionally, fusion devices can't melt down like a fission reactor. Fusion uses minute amounts of fuel at any given time, and you can immediately stop the reaction by cutting off the fuel supply. Additionally, fusion creates far less radioactive waste than fission. Spent uranium fuel rods are highly damaging biologically and remain radioactive for thousands of years, requiring complex disposal and storage methods. The radioactive waste products of fusion consist mainly of irradiated components. They're generally less dangerous, and the radioactivity dissipates within 100 years. A safe, low-cost, zero-carbon energy source like fusion can enable exciting possibilities for the future. So what would a world with commercial fusion power look like?
Throughout the world, we see challenges in water. So all of a sudden, desalination plants become really cost-effective and possible to solve some water challenges.
Fusion power can also help ease the transition to electric transportation. It's projected that nearly half of all cars will be battery electric vehicles by 2035. Additionally, the deployment of small modular reactors can allow for flexible placement of power where it's needed most, such as isolated areas or unique industrial applications, like for example, Tesla's Gigafactory. It's often said fusion power is 30 years away and always will be. Will fusion power be part of our electric future? If we compare the progress of fusion power to computers, a powerful trend emerges. Moore's law observes that the number of transistors in a circuit doubles every 2 years, and we've all seen the rapid advancement of computing power in the last half-century. For nuclear fusion, the triple product serves as the key figure of merit, and it's growing at a similar rate to computing power. It appears probable someone will demonstrate net electricity from fusion this decade, and Helion is a promising contender. But this is just the start. Turning fusion power into a competitive, cost-effective, real-world technology is going to be a long road. Despite the challenges, harnessing the power of the stars and offering mankind unlimited clean energy is a goal worth striving for. The work that goes into nuclear fusion power draws on all the branches of science, technology, engineering, and mathematics. If you'd like to better understand some of the concepts we presented in this video, it's important to first build your tree of scientific foundations. Brilliant does a great job of taking complicated science and breaking it down into bite-sized pieces with fun and challenging interactive explorations. Master concepts, learn the fundamental principles, and develop your intuition so you can truly understand these breakthrough technologies. I've taken Brilliant courses on electricity and magnetism and solar energy, and was impressed with how well they structure their lessons with clever analogies, examples, and quizzes to test your knowledge. Brilliant offers a wide range of other content and topics from mathematical fundamentals to quantitative finance, from scientific thinking to special relativity, from programming with Python to machine learning. Go to brilliant.org/electricfuture and sign up for free. And also, the first 200 people to go to that link will get 20% off the annual premium subscription. Electric Future presents optimistic but realistic coverage of breakthrough sustainable energy technology. If you enjoyed this video, please give it a like and subscribe to our channel. You may be interested in watching one of these videos next. Thanks for watching, and let the volts be with you.